So mass percent is one way to numerically describe the concentration of a solution. The more common way is molarity. And so molarity is what we're going to talk about through the rest of the course more often than mass percent. Molarity goes back to that central concept of the mole. And I think I've said that a few times. Really, moles are all important in chemistry. So mass percent, useful, but it is not concentration as we typically talk about it. So molarity is capital M as a symbol. So we can say it's molarity. And it can be in units of M or moles per liter. Those are absolutely interchangeable as the units. So the variable, the concept, and the units. And so we're going to talk lots about molarity or molar concentration here. It can be calculated using the following equation. So molarity is the moles of solvent in the volume of solution. So it's always moles per liter, or it can also be written as just a capital M. Those are interchangeable. So the concentration or molarity of a substance is also in those square brackets. So if I wrote this, that's saying I meant to make it hydrochloric acid. The concentration of hydrochloric acid is 3 molar. And so always, if you're talking about concentration, you can put it in those square brackets. So this, as a short form, is talking about the concentration of HCl. When you make solutions in the lab, and you have seen M's written on different bottles perhaps in the lab, you use often a volumetric flask. So a volumetric flask is this wide bell shape, and it has a really narrow neck with the measurement marker on it. So that's the only gradation of measurement on a volumetric flask. And it's a really accurate way to measure the solvent or the solution, and also mix the solution up. And so in this, if you have a 1 molar sodium chloride solution, I could say that the concentration of sodium chloride is 1 molar, or 1 mole per liter. And so here we have another one down here. There's basically multiple ways of saying the exact same thing, which is always frustrating when you're learning. If I say that I have a 3 molar hydrochloric acid solution, what does that mean? It means that that's the concentration of the hydrochloric acid is 3 molar. Or I could say that there are 3 moles of hydrochloric acid in 1 liter of solution. Another way of writing is that the hydrochloric acid concentration is 3 moles per liter. The standard way of calculating this and dealing with it is kind of back to like the density triangle. So we have a triangle, and you have this in your formula sheets, that molarity is number of moles divided by the volume of the liquid. And so here we have, if I do this, molarity is in its concentration or molarity. Interchangeable words. And the units are the capital M or moles per liter. They're absolutely equivalent. Okay, so moles is the number of moles. We know how to calculate the number of moles if we're given a mass, and we're going to keep using molar mass. And then the volume, this is where it is a little specific. It's impractical in the lab, but the units for volume is always liters, because that's what's built into our concentration measurement or our molarity unit. It's moles per liter. Okay, so we're going to do some calculations with these. I'm going to keep that triangle up. Basically, the way triangles worked when we did the density is if you want to know the equation, you simply cover up the thing that you're looking for, and you look at the relationship between the other two. So molarity is moles divided by volume. If I covered up the moles, moles would be molarity times volume. And the third iteration of this, volume, would be moles divided by molarity. And so those are helpful, but I don't think that having them memorized is worthwhile. I think understanding that triangle can be useful, and I'm going to do some dimensional analysis here too. So let's take a look at what we have. So we have some questions here. We want to find the molarity of a solution if we make it with the instructions that are written out. So we have 0.5 moles of lithium bromide. So the number of moles is 0.500 moles. Okay. We have a volume of solution. So the volume is 150.0 milliliters. I like kind of gathering up my information. I don't have this in the right units. Remember, I said volume was in liters. And so I would have to convert this from milliliters into liters. I would slide the decimal place 3. I would divide by 1,000. However your brain allows you to do that. I would have my volume in liters like that. If I want to calculate the molarity, molarity is number of moles divided by volume. I could write out my equation, and then it's simply subbing in and solving. What I'm solving for is the concentration of lithium bromide. And so I'd have 0.500 divided by the 0.1500. I'm going to correct to 3 sig figs. And so I would say that the concentration is 3.33 moles per liter, or the molarity is 3.33. Let's try some more of these. I'm rolling past my triangle, so hopefully that's okay. Now it says that I have 5 grams of KCl in 100 milliliters, of solution. So my number of moles can be calculated if I have 5.00 grams of KCl. If I figure out the molar mass, I didn't leave myself enough space, of KCl, I can calculate the number of moles. So I should finish this up. What is that? 39.10, or total 74.55 grams per mole in that compound. And so 0.55 grams, and that allows me to calculate my number of moles. I'm going to leave this in my calculator, but just for clarity and transparency, I'm going to put down some of the numbers. Okay, so the other thing that I have is a volume here. So the volume is 100 milliliters. I have to convert that into liters or it doesn't work in my equation. Whoops. So 0.1000 liters. So again, I'm trying to calculate concentration. So molarity is equal to the number of moles divided by volume. In this case, it's that number in my calculator. If you want to store it and recall it, go for it. It went on longer than I wrote. And divide that by your volume. So in this case, what we're solving for is the concentration of potassium chloride. And if I do this work, the concentration of the potassium chloride is 0.671 moles per liter, or it has a molarity of 0.671. Okay, there's another one here. You could pause the video and try this one on your own. We're going to make a solution with 6.25 grams of sodium carbonate, so that's NaCO3, and carbonate is a -2, so it would be Na2CO3, in water to make this volume of solution. So I'm going to need the molar mass of this because I was given the grams of it, so it's 3 times 16, and 1 times 12.01, and 2 times, so tedious to do, the molar mass of sodium carbonate. So now I know if I want to figure out my moles of sodium carbonate, right, I'd have 6.25 grams of the sodium carbonate. And I can use my molar mass to convert to number of moles. I'm going to keep this number in my calculator. I'm writing it out in the notes here just for transparency. Whoops, I forgot a zero. So 0.0589678, blah, 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 blah. The volume was just given to me straight up, but again, it's not in liters, so I can transpose that into liters before I just sub it into my equation. I'm just going to scroll so I have room to finish this, barely. Concentration is equal to moles divided by volume. In this case, it's the concentration of the sodium carbonate would equal that number that's still in my calculator, hopefully, divided by the volume in liters. And that would give me then 0.236 moles per liter, or a molarity of 0.236. So the molarity triangle, we've already talked about it. The molarity triangle is fantastic. It really is a versatile problem-solving tool. Molarity can also be seen. You could also see molarity as a unit factor. And so in the notes that are on Moodle, I do show both ways. In the video, I'm going to show you, instead of using the triangle, how we could see molarity as a unit factor. As an example, 3 molar is 3 moles per liter. So as a unit factor, that means that there's 3 moles in 1 liter of solution. And so by arranging this how I need to, I can use my molarity as a unit factor. Okay, so it says calculate the number of moles of NaCl present in 1 liter of 6 molar NaCl. So I could just take a look at this. Molarity would equal, number of moles would equal molarity times volume. I could just multiply these two numbers together. But like I said, we could see molarity as a unit factor. So this means that there's 6.00 moles of NaCl in 1 liter of solution. Okay, so I'm going to start with 1.00 liters, and then I can arrange this molarity as a unit factor. So I can see how it's, got messy. This canceling out would solve for moles of the NaCl, right? That's what I'm talking about. So whether you just multiply them and use your triangle or see it as a unit factor and kind of adhere to this dimensional analysis, that tells me that there's 6.00 moles in 1 liter of solution of NaCl. Sorry. Okay, that one was kind of intuitive, so let's try another one. What mass of NaCl is required to make 50 mils of a 2.5 molar sodium chloride solution? So what I'm suggesting here is that's 2.50 moles of NaCl in 1 liter of solution. So if I start with this in liters, that would be 0.0500 liters, right? You could totally do this with the triangle. If that approach sits better with you, you'll get to the same answer. I'm just suggesting it as dimensional analysis for the stoichiometry that's coming up. So in this one, I'm multiplying molarity times volume, same thing, right, as your equation. But it does allow me to see this dimensional analysis where the liters of solution cancel, and I've calculated the number of moles of the thing I'm looking for. And so in this one, it ends up being 7.31 grams of the NaCl. Okay, one last. Staying with this idea of the molarity triangle and seeing molarity as a unit factor. This one says what mass of magnesium nitrate, so MgNO32, take a minute with the nomenclature on that, is required to prepare 250 milliliters, so let's put that in liters, of a 1.50 moles of magnesium nitrate in 1 liter of solution. So we have a lot going on here. So we know if we start with what we know and use dimensional analysis, it can be a really powerful problem-solving strategy. If I want not the number of moles of magnesium nitrate, but the mass of magnesium nitrate, that means that I'm going to need to know the molar mass of magnesium nitrate. That would be 6 times 16, 2 times 14.01, and 1 times 24.31. So a total molar mass, 148.33 grams per mole. So watch how dimensional analysis can really kind of step things up. We're going to start with what we know, which is the volume, right? It's kind of backwards to the equation, but we're going to start with that because that helps us with the dimensional analysis. So 0.250 liters of solution. Sometimes I write in solution, sometimes I don't. Multiplied by the concentration as a unit factor. And we're specifically talking about moles of magnesium nitrate in 1 liter of solution. If I want to use my molar mass now, what I would write is 1 mole down below and the grams up top. You can do this as 2 separate steps, but dimensional analysis is so powerful. If I take a look at where I've gone with this, the mole or the liters of solutions went away, the moles of magnesium nitrate went away. I now have this in grams of magnesium nitrate. So if I multiply what's on the top and divide by what's on the bottom, it's actually all multiplying, I end up with 55.6 grams of that magnesium nitrate. So there's lots going on. I do think that a combination of the triangle and dimensional analysis are both useful, and I really would encourage you to find your sweet spot. You can do that last example in 2 steps for sure. That's fine. One last concept here. If we were to talk about something dissociating, there is another mole to mole ratio that affects the concentration. So we're just going to give 1 page of note here. If I were to talk about these, that compound, ammonium phosphate solution, it's going to dissociate into ammonium ions and phosphate ions. I'm going to start by coming up with the chemical composition. So NH4 and PO4. So the phosphate is a -3, ammonium is a +1. That would be the formula for ammonium phosphate. If it dissociates in water, that means it's going to have 3 ammonium ions, in solution, and 1 phosphate ion. The 4's always become 9's in solution. And so the 1 doesn't really need to be written there, sorry. The idea with this is that if we have this dissociation of 1 molar compound, it's going to adhere to the mole to mole ratio. So every 1 molecule of this is going to make 3 molecules of this. So it increases the concentration of these ions in solution according to that mole to mole ratio. So 1 mole of the ammonium phosphate would make 3 moles per liter of this ion in solution. It's not a complicated concept. In my experience, it's one of the ones that is kind of sneaky. We could write it in other ways. In Chem 12, I've seen this constantly be a problem. You just oversight, right? So that's why we've put it in the notes here. Those are the concentrations of the ions in solution. And so we've got a few more to do. Nothing too complicated. Don't overthink it. It is imperative that you get the right formula for these compounds. And I like writing out the dissociation because it gives me a chance to pause and really not make a mistake, hopefully, in this concept. This question says that the original solution had that as its concentration. So now I would just adhere to the mole to mole ratio. These are the same, right? The calcium ion and the calcium hydroxide, where the hydroxide ion is going to be double the concentration. And so really, again, you could just write it up here. The idea is that it's a mole to mole ratio in the dissociation of these compounds. So the last one, lithium sulfate. Take a minute with your polyatomics chart and get the formula for lithium sulfate right. Probably the trickiest part of this. And write out the dissociation of that ionic compound. Oops. If I start with a 1.50 molar solution, I'm going to have a different concentration of those ions in solution because of that mole to mole ratio or the fixed ratio in that compound. So I'd have twice the concentration of the lithium ion and the same concentration for that sulfate ion. You can really write this out as a mole to mole ratio if that helps you. Usually I find that kind of overcomplicates it for people. I did put it in the notes that are the answer key if you really want to check that out. But that kind of does our investigation into molarity and concentration.